Greetings everybody, so brand new topic on my channel today. I'm going to be starting a series on topological spaces and manifolds. So today I just wanted to introduce some of the basic definitions and axioms. So first of all, what exactly is a topological space? Well, as always, we're going to start off with a set, which I'll call M. So M, this is just a set. What is a set? Just a collection of things. Now, a collection of things is not too interesting to work with, or we can do basic set theory and whatnot, but it's nothing too interesting yet. Now, if you watch my videos on vector spaces, for instance, well, you'll know that a vector space, we always, again, start off with a set, and then we add on additional structure to it to make it a bit more interesting so we can do more things with it. And if you've seen group theory before, you know you also start off with a set and add on extra structure by defining some kind of composition map. So we're always adding on extra structures to our sets over here to make them more interesting so we can do more things with them. Topological spaces, they're no different. We, again, start off with a set, and we're going to add on this special structure called a topology over here. Now there's a couple of different symbols for the topology that I've seen. I'll just use tau because it seems like the most common one. You could always use curly O for, which stands for open sets, which we'll discuss later on as well. But the pair M and tau are set together with some topology. This whole entire thing over here is what's called a topological space. Now, I haven't even told you what this topology is. This topology tau also has to satisfy certain axioms and so on, which we'll cover later. But this topology, you may be asking, what does this even do on our set? Why do we even need a topology? Well, it gives us a couple of very important ideas. First of all, probably the most important one is the concept of continuity. So adding on this topology onto our set allows us to talk about continuous maps. And another idea that it also gives rise to, which I think is a bit more easier to grasp if you're seeing this topic for the first time, is the idea of neighborhoods. Now, this concept of neighborhoods, basically all it is, it gives you an idea of, well, in the set, what points are near other points. And this makes perfect sense why you would want to put a topology onto a set, because what is a set? This collection of random points in a big bag that can be all jumbled up whatsoever. If they're still in the bag, then it's still the same set. Now, this neighborhood kind of adds a bit more extra structure onto your sets. These points, they're going to kind of, you can think about it as kind of rearranging a little bit so they're in their correct positions. Now, one way you could define neighborhoods is, well, you could say, well, I want to know how far 2 points are away from each other. Is there a way to define some kind of distance between 2 points so I know how far each point is away from other points? And that's actually the concept of a metric spaces, where we actually assign certain distances to each of these elements over here and so on. So a metric space might be something I cover later as well, but it turns out the metric space is a bit too much structure because you're already assigning fixed distances between points. Now, we don't really care about how far points are exactly away from each other. We only care about roughly what the neighborhoods of the points look like, which means these points over here, I should really call them elements. But in this picture, maybe it's easier to think about them as points. These points, they can move around roughly. They can kind of be stretched and squeezed and so on. They're kind of like an elastic sheet over here. You can stretch it and squeeze it and so on. That's what an idea of neighborhoods give you. If you put a metric onto this set with all these points over here, you're kind of freezing out. You're putting fixed distances on all the points. So this kind of becomes like a biscuit, whereas if you're allowed to stretch and switch things where all the neighborhoods, they're still roughly there, this is more like some kind of jelly. Now, contrast that to just a set where you just have points in a big bag. You don't even care where the points are relative to each other. This will just be, for example, a bag of sand. So you put the topology on, becomes more like a jelly, but if you put a metric onto it, becomes a very nice crisp biscuit, but we don't really want the biscuit yet. We only care about the neighborhoods. That's why the jelly is a little bit nicer. This is kind of like the idea of topological spaces. You're defining what these neighborhoods are around these points. So, well, essentially you know what is near what. So that's very roughly speaking, just to motivate these definitions and axioms a little bit. Now, maybe a bit more motivation to go before we jump into definitions and whatnot. Consider just maybe a strip of paper or something, and we're going to kind of transform this paper into three things. First of all, let's just leave it as it is. So this is paper over here, just a sheet of paper. And another thing we could transform it into is, let's say we glue one edge to another, that would become a cylinder. And so let's say maybe we glue it to the other side, but then we introduce a twist into it. And that would become, if you've seen it before, that would be exactly a Mobius strip. Not too sure how to draw that properly, but something like that. That's a Mobius strip. And what we start off with, well, don't even think about this as a piece of paper. Just think about it as a set. Just think about it as a bare set with nothing else. It's a little bit hard to represent it, but really just think about it as just a bunch of paper particles all in a bag. So all these paper particles over here, yeah, they're just in a bag. It's just a set. You don't even know where the paper particles are. All you know that they're in this big box over here. So down here, I've drawn kind of 3 different scenarios, and each of these you can actually construct from this set. Because after all, they contain all the same pieces of paper particles and whatsoever. You can make it, well, from the same stuff. All these paper particles, think about it as just a set. Now, as you can see, from the same set over here, we were able to construct 3 completely different objects. And the question is, how were we able to construct these 3 different objects over here? It's by introducing a topology. Because what the topology done, remember, it gives us the idea of neighborhoods. So on the piece of paper over here, where you have all these nice neighborhoods, roughly you can think about it like this. Now on your loop over here, the neighborhoods, well, they're basically the same as the paper, but an extra thing you do on the loop is that, for example, let's take this point on the edge over here. This point on the edge on the piece of paper, the only neighborhoods, well, they're the other points around here. But on the loop now, since you're gluing this edge over, now the neighborhoods of this point, it's also included on this other side as well. So as you can see, even though if you just look on a small portion on the paper and on the loop, the neighborhoods look the same because it's the same kind of 2 dimensions. Globally, the neighborhoods are completely different because on the piece of paper, these 2 areas are kind of pretty far away from each other. But whereas on the loop, these sides are kind of associated to each other. So what you can do, you can walk along this edge over here and then suddenly appear on the other side. And of course the same goes for these bottom corners as well and all along these edges. So as you can see, since we chose different neighborhoods on our paper and our loop, it gives us completely different shapes. And also you can do the same for the Mobius strip as well. On the Mobius strip, instead of associating this area over here with this area up here, you associate it with an area down here. That's how you encode the twist into it. If you take this edge and twist it and glue it onto the other edge, then the neighborhoods are going to be completely different, both from the paper and the loop. So this topology over here gives you the idea of neighborhoods, and on a set, you can choose different topologies on a set, and that's going to completely change the structure of that set. So that was kind of my motivation, where we take a look at topology being something we can use to define these neighborhoods, which greatly change what your set looks like. And just one more thing that I forgot to mention in the original recording is the idea of topological isomorphisms. So you might have seen illustrations of where you have a coffee mug over here, and they say a coffee mug is equals, in a way, to a donut. Now these 2 objects, as they are, they're completely different. This is a coffee mug, that's a donut. But in the eyes of topology, they are the same thing because you can kind of deform this coffee mug, you can pull up the base and kind of smush it around a little bit and turn it into a donut. Now, notice why these 2 are the same in terms of topology. It's because topology is only concerned with neighborhoods. And remember, if you have neighborhoods, you're not putting fixed distances on everything. You can kind of stretch and squeeze things around, and you can turn the neighborhoods of the coffee mug into the neighborhoods of the donut, roughly speaking. And we call this a topological isomorphism, or a better name is a homeomorphism. So if 2 spaces are homeomorphic, then there exists a bijective function f over here, which preserves the neighborhoods of these 2 spaces. And this is what we call a continuous function, because as you can see, we can deform the coffee mug nice and continuously into the donut. And if you've watched topology videos, you might have seen those funny illustrations of things not being continuous and whatsoever. For example, if you have a loop of paper over here, and this is not homeomorphic to a rectangle, because you can't deform this in a nice and continuous way to get to the rectangle. You have to make a cut along here or something, and making a cut that destroys the neighborhoods, so the neighborhoods aren't preserved. So we'll make these ideas of continuous maps and homeomorphisms much more precise in a later video, but this is the idea of how it relates to neighborhoods and all that. Okay, so enough motivation and whatnot. Let's jump into some definitions. So a topology, we know it gives us rise to neighborhoods. And the way we define neighborhoods, you might notice I drew these little circles over here. Think about those circles as subsets. So what this topology is, you can kind of think about it as a list of chosen subsets of M. And in particular, what do I mean by a list? By a list, I mean precisely a set. So topology this tower over here, you can think about it as a set, a big set. And what you put inside of these sets, you put these little neighborhoods of your set M. So each of these little neighborhoods that I draw over here, you put them into your topology, and each of these, they're going to be subsets of your original set M that you have. So the topology, it's simply a list of all of these subsets that you call the neighborhoods. So another way to say this is the topology is in fact a subset of the power set of M. Now, if you haven't seen the power set before, the power set is simply defined to be the set of all subsets of M. So what I mean by this notation is that take any U you can think of that's a subset of M, and then collect all of them into one big set. That's the power set. So a very simple example, let's consider this set M is equal to 1, 2. What's the power set of M? Well, the power set of M, well, it's a big set over here. What do you put inside of these sets? All the subsets you can think of from here. So what are the subsets? Well, first of all, the empty set is in there. The whole entire set is a subset of itself, so the set 1, 2. What other subsets you have? Well, we have the subset containing 1 and the subset containing 2. And important to know that you don't want 1 and 2 inside of the sets, because 1 and 2, those are elements of M. These are not subsets, so they can't possibly be in your power set. So the power set only contains subsets. So this is an example of a power set. So notice the power sets list all the possible subsets of your set M. But with the topology, you only choose certain ones that you want as neighborhoods. So that's why the topology, it's only a subset of the power set. You only choose maybe these ones over here. You only choose a part of the power set. So that's what the topology is as a set. And this also has to satisfy some conditions. So which satisfies the following axioms. Now there's actually 3 axioms to a topological space, and I think it's a little bit better to go in the opposite order. It's a little bit weird, but I think it makes explaining them a little more easier. So let's say this is our set M over here, and we have a bunch of these neighborhoods as I've illustrated before. So notice if we have 2 neighborhoods over here, then their union over here, if we take 2 neighborhoods and combine them together, that must also be a neighborhood. So the way this axiom is usually stated is if you have a collection of sets called U alpha that are neighborhoods. So if they're neighborhoods, they're already in this topology over here. So you can pick any neighborhoods that you want from your given topology. Then this implies that if you take the union of any neighborhoods that you want to, then this must also lie in your topology. So what do I mean by these little alphas down here? Alpha, that's just an index, and this A, that's an index set. So you can choose to index your U any way you want. So let's say we have a bunch of neighborhoods over here. You could call this U1, U2, U3, U4, for instance. If you take the union over all those alpha values, then the whole entire thing, if you union them all together, it must also be another neighborhood. So this whole thing over here must also lie in your topology, in your list of neighborhoods. Now A, there's no restriction on A. So this A over here does not only have to be finite, it could be infinite as well. So you could union infinitely many neighborhoods together, and the whole entire thing must also still be in your topology. But worse still, it could be uncountably infinite. So what I've done over here, we've indexed them by natural numbers, which are, well, countably infinite. But you could also index these by the real numbers as well, which are uncountably infinite. So you could have some kind of U1, you could have UE somewhere over here, you could have U pi, you could have U root 2 somewhere down here, you could have U minus 1. So this index could be anything. If you union all these together, it still must be in your topology. So we got the union, how about the intersection? And that's exactly the second axiom. If we take a look at the intersection of 2 neighborhoods, then that again must be a neighborhood. So if we have U and V that are already in your topology, so U and V are already neighborhoods in your list of neighborhoods, then this automatically implies that if you take U and you union it with V, then this must also be another neighborhood. So if you have 2 neighborhoods in your topology, in your list, then if you take the intersection, or that intersection must already lie in your topology. Now the first axiom over here, it simply states that the empty set, as well as the whole entire set, must be in your topology. So this should make sense because, well, this M over here, how do you get the M? You could just union all the possible neighborhoods you have together, and that should reproduce that M. So it makes sense that M itself is a neighborhood. And how about this empty set? Well, it makes sense because of the second axiom, because these two neighborhoods could be disjoint. So you also include empty sets as being the neighborhood. So if our topology, tau over here, satisfies these axioms, then the space M with the topology is called a topological space. So before we go any further with examples and so on, it's important to make a couple of definitions. If a subset U is in your topology, so these U's, we were calling them neighborhoods. So if we have some neighborhood, then we call this neighborhood open. So basically, whenever we have a neighborhood, that's how we used to think about it. Now we're just going to call them open sets. Now this has nothing to do with the open sets from the real numbers, and where we have an interval and we don't include the endpoints. In fact, the reason why we call this an open interval is because of how we define a topology on the real numbers. But this is just the label for these sets. We just simply call them open. It has nothing to do with endpoints or anything. Now another definition to make, if we have open sets, then we should probably have closed sets as well. If you take your whole entire set and you exclude some other sets, let's call it A, and this lies in your topology, then A is called closed. So for example, if this is your set M over here, and let's say you take a look at this set, which we call A. Now if we take a look at everything else besides that A, so if we take a look at this green subset over here, if this green subset is an element of your topology, so if it's an open set in particular, then that A is closed. Now it's important to note that open and closed really have nothing to do with each other. So if you have a set that's open, it does not mean that it's not closed. So a set could actually be open and closed at the same time. So open and closed are not mutually exclusive. And a very good example of this is actually the empty set and the set M. So the claim is that empty set and M are always both open and closed. So how do we show this? Well, let's start with the empty set. Clearly the empty set is an element of the topology. But notice M, if we take out this empty set, what is M without the empty set? Well, this is just M over here, but notice M, that's an element of your topology, which means by definition, this empty set is also closed. And you can also do the same with M as well. Notice what is M without M? Well, this is the empty set, but this is an element of the topology, which means although M is an open set, by definition, it's also closed. So empty sets and M, they're always both open and closed. It is possible you could have other sets which also have this property, both open and closed, but that always depends on what topology you choose. So if you choose different topologies, well, that has different consequences for these subsets. Another example is that a set could be not closed and not open. We can't really construct any examples now, but there are definitely examples where a set is not open and not closed. So the important note is that open and closed have nothing to do with each other. They're not mutually exclusive. So those were just some of the basic definitions I wanted to get through. And now for some actual examples. So an example, let's take the set M to be equal to a triangle, a circle, and a square. So this is just a set, and to turn it into a topological space, we need to construct some kind of topology over here. So remember, a topology, that's just a big set. It's a set full of these open sets. So from the axioms, we already know the empty set and M must be in there. So now remember, a topology is a choice we can make. So we can add any other subsets in here. We could have any other neighborhoods if we wanted, as long as they obey the second and third axioms. So for example, we could also include triangle and a circle in there. Maybe because we want to, we could also include a circle in there as well. And maybe we'll just finish off the list there. That's our topology that we choose. Now at the moment, this is just a collection of subsets. In order to ensure that this is indeed a topology, we have to check these three axioms. So of course, we check the first axioms. If we check the second axiom, you can check for yourself that this works, because if you take any two sets in here and take the intersection, it already produces a set that's already in here. Same for the union. You can take any arbitrary union in here, and you should find that we already have a set that's already in this topology. So what we conclude is that M, along with its tau, is a topological space. Another example to make is let M be any set. We can choose a tau to be, well, the set consisting of only the empty set and the set M itself. So notice the first axiom holds, 2 and 3 also hold, because take any union, take any intersection, it's already in there. This is what's called the chaotic topology. And it's chaotic in the sense because the only non-empty neighborhood, if you want, is the set M. So you can kind of think about everything being in the exact same neighborhood, hence the name chaotic. And another example to make is, again, let M be any set. You could choose a tau to be the power set of M. So remember we said that the topology was a subset of the power set. Well, you can definitely choose the whole entire power set to be the topology, and this is what's called the discrete topology. It's not too clear why it's called the discrete topology. It has to do with convergence of sequences. So the sequences only converge in this topological space if after certain points they kind of stay at the same point, so they have to be discrete after a certain finite time. And so that's why it's called a discrete topology. We'll cover convergence later in the series as well. But yeah, those are some examples. Maybe one more example, which will make more clear next time, is what's called the standard topology. So if we have R and we can choose tau to be what we call the standard topology. And the standard topology on Rn gives us the usual way we define continuity and convergence and all that kind of stuff we know from real analysis. But we'll take a look at how we construct this standard topology and what it is next time. But yeah, that's pretty much all for today. Hope you guys enjoyed this video, and up until the next one, have a wonderful day, and I'll see you guys later. Bye bye.